The link to the slides is j.mp pi hw-SyPy-1015. I realized afterwards that we're not in the 10th month, so it's a little bit confusing. It's on every slide, so you don't need to write it down right now. But first, if you're using dates in Python, you should be using my module. It's basically a date-time compatible module which deeply cares about time zones and like gets time zone maths as right as I can get it. So yes, Python datetime TZ. It works on Windows, Linux, Mac. I don't know, I haven't tested on Mac, but I assume it works on Mac. It does things like understand your local time zone on your system using a bunch of different methods to figure it out. Yeah, we have Windows support as of recently. You should be using this if you're using date times in anywhere in the world that has time zones, which I think is everywhere, sadly. The next thing, I didn't create this, but I help maintain it now. It's a package called Q. It's basically quick and dirty debugging for tired programmers. It's like basically doing printfs, except your printfs go to a file in TskPy, and you can printf pretty much anything. It's also a great example of what you shouldn't do in Python, because you can import a module and then use the module on something to print something, or use the module as a decorator, or use it to, yeah, it's horrible. But it's a great way to debug something when you're like 2 AM, you just want to put a bunch of print statements in, like your standard error and standard output going somewhere else. And it's like one file. So I highly recommend it if you're tired and want to get your stuff done. So back to the thing I was here actually for, designing hardware in Python. So I love Python. It's my favorite language. I love it so much I started a conference here in Australia for it. But I'm practical as well. Python is not the best language to do everything in. It's pretty good at most things, but if I was writing an embedded operating system, I probably wouldn't choose Python. Everything is not a nail, as they say, and Python isn't the hammer. Use the right tool for the right job. So the question then comes, why should we be using Python for hardware, and why am I talking about it? Python is a long way away from hardware. If you know anything about how operating systems or computers work, normally you don't have like methods on your integer object, and normally it's not like a full class object that you can do anything with. All these other things like memory management, that's a really nice thing to have in Python. The hardware doesn't actually have any memory management built into it for like garbage collection and that type of thing. So it is very different. It's also not a particularly popular tool to do hardware in. And I've learned for a long time that you should probably use the most popular tool unless there's a very good reason not to. I'm a Python person, but I use Git because, you know, everybody else on the planet uses Git. Mercurial is probably superior in pretty much every way, except not being as popular. So I would recommend using Git, because when you get an error, you can type it into Google and you get help for it, rather than just no pages found. So 6 months ago, I would have said, you're crazy, you shouldn't be doing this, why are you even standing up here? But now I say yes, and there's a reason why. I'm going to basically go through a case study of a project I work on called the HDMI to USB project, which is part of a bigger project called Tim's Videos that I run, all open source. The aim of the Tim Videos project is basically to do live event and user group streaming. And eventually, when I succeed in this goal, hopefully SyPy will also be live streamed and recorded and uploaded and all these type of things. In fact, at this very second, there is a Google Hangout, which you might be able to find if you're tricky, that is getting a recording of this talk. I have no idea if it's working because it's on my laptop and I don't play at that mode. But in theory it is. So how do you record stuff? You can run stuff on your computer, but that's not particularly friendly to the presenter who doesn't want to have to download random software onto their computer just to present at your user group. So the way we solve this is by basically putting a capture hardware between the presenter's laptop and the projector. So you can kind of see up here, there's the presenter, which is me at the moment, I guess, and there's the laptop, and you've got the cable that goes into a piece of hardware called the HDMI USB, and then it goes into the projector. And we capture basically what the presenter is projecting. And so as long as the presenter can project, we can capture it. And so kind of zooming in, we also have HDMI cameras. They basically work in exactly the same way. They're a HDMI device, except they only go into the HDMI to USB device instead. The reason we need this hardware is because basically commercial hardware doesn't allow you to understand what's going wrong. I'm sure you've been a presenter, you come up the front, you plugged in your laptop and gone, it doesn't work. And then you played around with it for, I don't know, 10 minutes, and eventually some combination of sacrificing, chickens and stuff like that causes the system to work. And that is obviously not particularly good. So we designed our own hardware to give us the ability to basically understand what's going on. Why isn't the presenter being able to get it? Is it the fact that he hasn't plugged in the cable, or they haven't plugged in the cable? I know I've done this before. You're like, why can't I see anything? It turns out the cable's not plugged in. Are they sending the wrong resolution? All these type of things. So we started creating hardware to do that. And our solution to that was to use a thing called an FPGA. Who here knows what an FPGA is? About half. So FPGA is basically a field programmable gate array. It's a piece of technology that makes hardware problems software problems. You write a hardware description in a language, you download it to the FPGA, and then the FPGA behaves like that hardware. It's a great way to not have to manufacture chips while still being high performance. So you can see on our boards here, there's the thing in the circle is the FPGA. There are two major languages used to program an FPGA. One of them is called Verilog and one of them is called Vhdl. Verilog is arguably the oldest, but the people who like Vhdl will say otherwise. It's got a syntax based on C and has had major revisions in like the mid-80s, the mid-90s, the early 2000s, and the mid-2000s. It's a weakly typed language. It's very compact, like C, and it has pretty reasonable open source support. There's a simulator for Verilog. There's some compilers. There's some tools for working with it. And that's one of the languages you can use. The other language is called Vhdl. It was developed in the military, so it's based on Ada. Who here knows what Ada is? About half the room. It's a language that they use in the military, and nobody else really uses. It's got lots of nice points and lots of horrific points. Vhdl was kind of a little bit later. You can see 1987, 1993, 2008. It's a very strongly typed language, which if you like strongly typed languages, you're going to love. But it's also extremely verbose. You end up writing the same thing like a bazillion times. It's got very poor FOSS support. There's not a lot of tools for working around it. There's not a lot of good simulators. However, it has this one really nice feature, which is it's 100% deterministic. If you go and read that link, it will give you more information about why Vhdl is technologically better than Verilog, despite it having all these other issues. So, like I said, I always tend to be practical, so I picked the most popular languages for doing FPGA programming. I picked both of them, apparently. I picked Vhdl and Verilog and a mixture of stuff that already existed in those things, connected it all together, and created firmware that does HDMI capture. It works on this board here, which is called the Vigilant Atlas board, and it kind of works. When you know all the planets align, it captures correctly. Turns out Vhdl and Verilog are very unproductive languages. It took us 3 years to get basic features working. We still had like a feature list as long as our arm of stuff we wanted to implement. Things like Ethernet support and double buffering. As well, there's not a huge amount of good libraries. Like in hardware, you need a lot of things like queues, like, pardon me, first in, first out queues. The way most people develop in this is that there are tools that you use to develop Vhdl and Verilog that come from the manufacturers of FPGAs, and they have a tool which lets you generate a FIFO, which is really great. It means you just like say how big you want the FIFO is and what device you're targeting, and it generates you a piece of FIFO. However, it's interestingly licensed. You're only allowed to use that generator code on hardware produced by that manufacturer. So if you want to use it on some other manufacturer's FPGA, you have to rewrite it, which really sucks because we're an open source project, and the reason we're open source is because we want to share with people. We want to collaborate with people who are using other FPGA boards and share systems between them. But because we were using a lot of this generator code, we couldn't. As well, hardware people do testing in a very interesting way, if at all. There are things called test benches, which are like really low level. They check that, you know, the output when you like one of these little lines goes high, that one goes low, that one goes low, these type of things. These are impossible to debug. They're impossible to maintain. They take like 20 hours to run. They're just generally horrible. And then we created some hardware. So this prototyping board we're using is not open source. It was just a board we bought off the shelf. We want to be totally open source, so we developed our own hardware, which is actually now crowdfunding on that URL there if you're interested in buying one. The thing was that it was very similar to our original board, but it was very hard to add support to our existing firmware despite it being very similar. And to do it, the code needed a lot of refactoring, and both Verilog and Vhdl don't have really great ideas of doing things like templating or subclassing or anything like this. So it was really hard to support 2 boards. And then one day when I was searching on the net, I came across these 2 other projects called the Milky Mist and the Mixio. They're very, very similar design to our board. They have the same FPGA, which you can kind of see here in the center. They have HDMI ports like us. The thing is, they don't do any capture. They just do like video mixing. They're more for like video DJs and things like that. But the very interesting thing about it was they developed their own language called MeGen and their own set of libraries called MeSoc. And that was Python based. As I said, they already had HDMI systems working. They had the DDR RAM systems working, they had Ethernet working. The really interesting thing is that they supported the Milky Mist and the Mixio boards, but they also supported like 18 other boards, like just general boards that were out there. So this was kind of very interesting. Why not try Python? I much prefer Python, and C and Ada are both horrible things to emulate, and they didn't do it very well either. But I'm skeptical, right? Like, as I said, I'm a practical person. There needs to be a very good reason why I don't use the most popular thing, because I want to type into Google the error message I find and come up with help rather than no hits found. So the first question is, how do you run this Python on an FPGA? And it turns out that they don't. What they do is they generate Verilog, which is equivalent to the Python, and then use the Verilog to compile down to what runs on the FPGA. So they don't need to get toolchain support via these vendors. They just can generate Verilog code that the compilers understand. The other interesting thing I found was that it turns out computers are better at writing Verilog than we are. Verilog is very much a language where consistency helps, and not things like state machines and stuff like this. It really helps if you line up your code, you have very consistent indenting and all these type of things. That's much easier for a computer to do than a human to do, especially a human who's an electrical engineer and doesn't really like programming software. So that was interesting. So I basically got a group, and is mainly a single guy in France called Florent, who works for Enjoy Digital, to try and re-implement our firmware that we already had that was mostly working if things aligned properly. And I gave him kind of a deadline of about 4 weeks to do it. That's about how much money I had saved up that I could afford him to do it. And he did it. That URL there is basically the firmware that replicates the functionality that our old firmware did in Python. The really interesting thing is in his 4 weeks, we got a lot more features. We got double buffering, which means that when I switch the output of this FPGA between the inputs, it doesn't cause a discontinuity. He supported both our boards straight off the bat. It has an internal soft CPU, often called a soft core internally. He did Ethernet support. We had a student work on Ethernet support for 3 months, almost full time, to tell us whether Ethernet support was possible or not. He did Ethernet because it was an easy way to debug what was happening inside the FPGA. So he didn't even do it because we asked him to do it. He did it because it helped him get the rest of the stuff done faster. As well, it has a soft core in it, which was really interesting. We'd never had a soft core in our previous firmware. Going quite a lot over time, so I'm going to try and speed up. To write code for the soft core, you write in C, not Python, sorry. But you compile it with GCC and you download it into the FPGA. So you actually download things twice into FPGA at the moment. But this update is really quick. GCC, like compiling a small program, takes like a second to do. Whereas compiling for FPGA takes like, I don't know, a good 15, 20 minutes on a good day. So all of a sudden we can develop functionality with turnaround cycles of a second rather than turnaround cycles of 15 to 20 minutes. It did have some downsides though. The big one was because it had a soft core, we needed a custom GCC and Vnto tools to get started, which means that people not only had to install the FPGA tools, they also then need to install these tools. The community is small, it's like maybe 100 developers, so there isn't anything on Google. It was also interesting that this isn't the only people doing this. There's another, oops, sorry, I've skipped ahead. So to compare, our old firmware was written in Vhdl Verilog, was hard to understand, had questionable licensing around it. Our new one is written in Python and C, has more functionality, and the other great thing is that all the cores that you're using are completely open source because the other one generating the code, not this piece of FPGA compiler technology. So it's actually truly open source, and we can run it on any FPGA we want. We don't have to be restricted to just the one toolchain we're using. So things are a lot more awesome. A lot more progress has been made in the short period, and we're actually starting to use it in production. There's a conference in South Africa at the moment, which is currently trialing these boards. I'm running it here. Broadcasting to a Hangouts on air. So yes, you can build hardware in Python, and it works really well. And it turns out, well, the MeGen guys aren't the only ones doing it. There's also a group called MyHeatShield, which are also doing Python stuff to Verilog and then compiling it down. They've actually had, the MyHeatShield guys have had stuff end up in like real hard circuits that you can find in computers and stuff like that. So they've had quite a bit of interesting success as well. I promise I'm not going to be a huge amount longer, but I still have some more to talk about. Because it turns out Python isn't just useful in that case. It turns out that actually creating the circuits, Python is really useful. So to create a circuit, you first start with a schematic, which is basically, you know, like the electrical connections of how you connect the ICs together and like resistors and things like that. And then you create what's called a PCB, where you put all the chips on like a physical space and draw the connections, like where the wires are connecting and that type of thing. There's a really good open source program for doing that called KiCad. To do this professionally, you're probably using a tool like Altium. Altium starts at $5,000 per license. This is free. There are cheaper tools for doing it, but they're very restrictive in what you can do. Like, you can only do very simple boards in them before they start asking you to pay thousands of dollars as well. So KiCad is really awesome. And that board I talked about, that open source board, we designed in KiCad. So it kind of proves that KiCad can be used for a pretty complicated board. This is a board with, you know, 2 HDMI in, 2 HDMI out, USB, Ethernet, DVR, RAM, DisplayPort in, DisplayPort out, all these type of things. It's a reasonably complicated board. And we did it in KiCad. It's published on GitHub. It's under Creative Commons share alike type license. And yeah, again, If you want to support open source hardware, you can go to this URL and help support us. KiCad, it turns out, is really scriptable. You can write plugins for KiCad in Python. We didn't use this ourselves, but I have known other people who have done that. Quite useful. The other thing is KiCad, being an open source tool, has all its file formats in plain text. And everybody knows Python is like super dealing with plain text. It loves reading things like CSV files. It also loves reading KiCad formats. So for these boards, that FPGA, because it's so reconfigurable, doesn't know what each of the pins are connected to, because the pins are connected to the ports, like the HDMI ports and stuff like this. But you could casually change the design and connect them to a different port. So there's a thing called a UCF file, which tells your firmware how the FPGA is actually done on the board. Normally these are generated by hand. And one thing that are really common about is that you get one from a manufacturer and they're full of errors, like things are around the wrong way and they're not connected up as they say. And that's kind of a pain to maintain when you move stuff around. So we wrote a tool that was kind of hacky to generate the UCF file from the schematic. The schematic's like what we use to manufacture. So as long as our script is right, we don't get human errors introduced into the UCF file. And when we update things in our schematic, we just rerun the script and we get a new UCF file. So this is pretty awesome. I've also been developing the idea of circuit unit tests. It turns out that there are a lot of things in hardware that you shouldn't do. I.e., you shouldn't connect your power rail to ground and try and short that. But there are a lot more complicated things that we can do, like high-speed signals shouldn't be routed near low-speed signals. They should be the same length, things like this. And the tools don't let you express that information very well. So I've been working on these things called circuit unit tests, which is basically a tool you run over, you make changes in your schematic, and then you go Python unit test, and it tells you whether or not you screwed up your schematic or your PCB. And it understands things at a much higher level than you normally understand things. So yay, Python is actually really great for really helping build hardware. But there's still more, and I'm running way over time. Talking hardware takes normally two forms, USB or serial. Turns out Python is great at both. There's a library called PyUSB. It's pure Python using C types, using any one of these libraries as kind of the back end if they're installed on your system. Supports pretty much every version of Python I care about. Windows, Mac, and Linux. This is kind of what the code looks like. If you understand USB, you will understand what that means. If you don't, sorry, but I don't have enough time to explain it. There are a few little problems with using PyUSB. Generally, you need to run it as root unless you've set up permissions properly with UDEV rules. On Windows, it's mostly fine. There are some corners. I have no idea of Mac or BSD. I don't run any of those systems. So it can be a little bit tricky for that reason. Again, this board. On this board, we have this chip here, which is not the FPGA. That's the FPGA. This is the USB chip. It's basically a USB chip that can emulate a whole bunch of different functionality. It can be a serial port. It can be a JTAG programmer. It can be a webcam. So this is kind of complicated. So I've been running a PyUSB tool that detects the board and lets you switch which mode you want it in. Do you want it in the JTAG development mode, or do you want it in, you know, the webcam mode, or that type of thing? And PyUSB was really great for doing that. The thing is, when the board changes functionality, it disappears and reconnects as like a different device. And as far as like your computer's concerned, it really is a different device. So you need some reasonably complicated logic to go, no, actually it is the device that I just told to disconnect and reconnect. And Python is really good at that type of thing. I seem to have that slide twice. It turns out though, most of the time you don't need to deal with it at the USB level, because most of the interfaces are actually just USB to serial converters. Who here knows what serial is? That's great, most people. So that's what you used to have on the back of your thing that was called a COM port. PySerial is a great way to interface to serial ports. It supports more Pythons than I care about. Python and IronPython, if you're mad for some reason. Supports all the different things. And as you can see, it's pretty simple. You just import the serial module, then you write some stuff to it, and you close it, or you read some stuff. Pretty simple. Remember how I said we want to control over our board? This is how we do it. Our board appears as a webcam and as a serial port. And you can connect to the serial port and you get this type of interface, which looks like a command line interface. And you can change stuff. And I can actually show you that. If I move my... So this here is the command line interface, and I can type help, and so I've got a video matrix, and I can connect input, let's do pattern to output 1. And output 1 is this little thing here, so that can do anything that you can see. Output 2. Sorry, output 0. Where is it gone? My mouse. Video matrix connect. Pattern output 0. There you go. I'm just going to put that